All right, folks. The last video was pretty short. This one should be pretty short too, and we are still on. We're still on the slide. We're on slide number 9 now, and this is an example with a large equilibrium constant, and I'm pretty sure your book doesn't do these. So we're doing a little bit more than the book does. We can find some supplementary videos, but I have a feeling we're going to be doing some tutoring with these ones. And I call this pushing equilibrium. I don't think anybody calls it that. And number 16, there's a couple problems like this in the homework, but number 16 in the homework, I'm just looking at it real quick. If you can do that one, you understand a lot about equilibrium. It gives us, and it's a large equilibrium constant. I'm looking at it right now. It's 5.6 times 10 to the 7th. So that's a big one. That's not like a weak acid or a weak base or anything like that. That's a good problem, and there's some other ones in there that kind of takes you through when do you use the 5% rule, when do you not, when do you push the equilibrium, when do you not. So, but that may take some time. Okay, so we're going to do one here with something you kind of know about a little bit, and I'm going to walk through this one fairly carefully. And you might remember complex ions where you have ligands. So we're not going back and do all of that. That was kind of earlier in the semester. So, and this is all homogeneous, so we're not throwing that in there. And so again, it's already on the problem, I think. Complex ion formation. Okay. So we're, let's see. In this case, we're taking nickel with a positive 2 charge and 6 ammonia ligands. It's a monodentate ligand, and it's an equilibrium with a complex ion. And we did all this early in the semester. So this would be an octahedral structure, but for this problem, it really doesn't matter. So this is an equilibrium of a complex ion. Okay, that's fine. And I'm going to try to make this, my notes seem like they're a little confusing here. I don't know why. And Kc for this one would be, let's see, nickel times NH3, or not times, just that, over nickel plus 2. I'm not putting AQ. And NH3 to the 6th power. Automatically, math, when we look at that and go 6th power, what are we going to do with that? Well, we're going to simplify the math. We're going to set this problem up so that we have a small x. But x will not be small at first in this case because it's a big equilibrium constant. So the value for this you're given is 5.5 times 10 to the 8th. And that would be some crazy units. That would be, I guess, inverse molarity to the 6th power. Yeah, but I'm not going to bother with the units on this one. Obviously, I'm going to just throw this in here. For complex ions, this is called a formation constant. It's the same thing. Kc is just generic for using concentration polarities. For an ion, it's called a formation constant. It's a formation constant for the complex ion. Some tables that you may look up later on in the semester may have KFs. Okay, so that's really big. Excellent. And what are we given in this problem? Calculate the equilibrium concentrations of all species if you start off with, okay, 0.25 moles of nickel are added to, sorry, I almost logged off there. 0.25 moles, okay. So I'm just a little sneaky on, oh geez, okay, I'm a little sneaky on the math here. are added to 1 liter of, okay, I'm not gonna go through a ton there. All right, okay, so what are we gonna do with this one? Well, we have to do a little bit of work here, because if we do an ice table and then we're given initial information for initial concentrations here, and we have to go the whole, wow, okay, this is gonna be a little rough. So before we do an ice table, I think this method might seem a little confusing at first, but it's a really good way to do it. Okay, what we do, let me just explain what it is we're doing. So we've got 0.25 moles, right, of nickel are added to 1 liter of 2 molar ammonia. So that's easy. So we have 0.25 moles here and 2 moles here. It's 1 liter and 2 molarity. That's pretty cheap. What we're going to do is this equation, this is not new. Most all of that is going to turn into this complex ion because this is so huge. So what we're going to do is use stoichiometry and push everything to the right. Then we're going to end up bringing it back. So bear with me on this one. And this is what's called an if table. Initial, final. It's stoichiometry, it's not equilibrium. And it's just using moles, it's not using molarity. So just bear with me, it's not the same thing. So what we do here is, I'm gonna see if I can actually put this, well, I'll rewrite it. These are moles. It's kind of like stoichiometry where we're gonna take the reaction to completion. Actually, that's a great way of looking at it. Because it's a big equilibrium constant, the reaction's pretty much going to go that way anyway. So I'm just going to rewrite this. I'm going to skip all the A and Q stuff. We know it's homogeneous. I have a tendency to make these problems harder than they should be. Okay, so we start off with 0.25 moles. It's an if table, a little different. And we start off with 2 moles of ammonia. And nothing here. Okay. Well, what's going to happen here? This may take some time. Okay, so we're going to push everything that direction. So how much of this stuff's going to be left over? Well, this is kind of stoichiometry. Follow me, see if you can follow me here. We have 0.25 moles of nickel. We need 6 times as much ammonia as we do nickel. We don't have anywhere close to that. Ammonia is our excess reactant here. So if you take 0.25 times 6, you're going to get something a lot less than 2. So this is your limiting reactant. So if we push everything to the other side, there isn't going to be any nickel left. And since it's a 1-to-1 ratio, all of that nickel is going to turn into the complex ion. It's a 1-to-1 ratio, so kind of follow me here. And then how much of the ammonia is going to be left? Well, it's going to be 2 minus 6 times 0.25. Well, this is going to go down by that ratio. Okay, does that make sense? So we're just doing the stoichiometry. This This is your limiting reactant. It's a 1-to-1 ratio, so you're going to produce 0.25 moles here. And how much of the ammonia is going to be left over? 0.50 moles. 0.50 moles. Now remember that because I have to erase this information. So now what we're going to do? Is set up an ice table. But an ice table involves molarity, so concentration. So we're going to take all these moles and make them into concentrations. And what's the volume? Oh, well, the volume is easy. It's 1 liter. Well, that's easy. So if everything here is 1 liter, this is the initial concentration of the ice table is going to be 0 molarity, 0.50 molarity, and 0.25 molarity. They're not always that easy. Just make sure that you divide. So divide moles by volume in liters to get molarity for the ice table. That's going to be true for the problems in the homework. So I made this one pretty easy, okay? Maybe too easy in terms of that. So if it was 1.5 liters, you would just divide those all by 1.5 liters, but to make the point. So that's the next step, and let's set up the ice table and do it. Because now we've actually made the problem pretty easy if you get to this point. So that's step 1. This is what I mean by pushing the equilibrium. We push it completely to the right, then the ice table, we bring it back, and our x is going to be really small. So let's leave that there. I put step 1, push it. This is step 2. Our ice analysis. So we've recognized that it's a large equilibrium constant. Some of the homework problems are like this. We push it completely to the right. I think there may be one where you push it completely to the left because it's a small equilibrium, but anyway, you'll get that. The initial concentration here is 0. The initial concentration for the ammonia is 0.50, and the initial concentration here is 0.25. Excellent. Now we're kind of home free, I think. And wow, this is the 5%. The 5% rule is going to be absolutely necessary. I don't know about you, but I do not want to solve an equation that has an x to the 6th power in it. But we're not going to have to. If you got this far, the rest of this problem is pretty easy. This equilibrium has to shift to the left to happen. So this has to go up by x. This has to go down by x. And this has to go up by 6x. Okay, so that looks kind of like a pain. Well, that's actually not going to be a pain at all. So the equilibrium concentration of nickel is going to be x. The equilibrium concentration of ammonia is going to be 0.50 plus 6x. And the equilibrium concentration of the complex ion is going to be 0.25 minus x. Oh, well, hold it. I still have the number up there. That's good. Well, let's put in some numbers and see what happens. So we're going to have 5.5 times 10 to the 8th equals 'the complex ion in the numerator times nickel in the denominator, and then 0.50 plus 6x, and check this out. This almost looks like it's going to be redundant. That has to be raised to the 6th power. Why did we do all of that? Well, we did all of that because we're going to assume now, because we pushed it and are bringing it back, the equilibrium constant is so big that x to come in this direction now is negligible. It's negligible. So we're going to assume that that is approximately 0. I really should have said approximately 0 before, not 0. And we're going to assume that it's approximately 0 here as well. I think this is the first problem where we've made the assumption in two different parts of the math. But we're going to assume it's so small that it's small here and it's small here, but this one we have to leave. We can't assume that's 0. That would make this problem ridiculous, and we couldn't solve it that way. So this actually simplifies to 5.5 times 10 to the 8th equals 0.25 over x times 0.50 to the 6th power. Wow. But you can do that, can't you? You can solve that for x. So multiply each side by x, so bring x over here. Divide through each side by this. I'm going to let you solve that now. Just don't forget to take this 0.5 to the 6th power. That is really, really important that you do that, else you won't get the right answer. In this case, you do all your math. See, you can let me know if you have any questions. 2.9 times 10 to the 8th, and it's always a molarity. I'm sorry, negative 8, which looks really, really small, which was the whole point. Okay? Does the 5% rule apply now? 2.9, yeah, it does. 2.9 times 10 to the 8th molarity. Now this always is fun. Compared to what? Because we can compare it to the 0.5 or the 0.25. Well, let's pick the worst case scenario. Let's take the smaller concentration to put it down here. Well, you don't have to do this math. Well, you should do that. You should do the math. But if you take 2.9 times 10 to the minus 8 divided by 0.25 or 0.5, it doesn't matter, times 100, yeah, you get a ton less than 5%. So the 5% rule works, which again is why we did this. So now the final step is, what are the equilibrium concentrations? Take that value for x. Okay, well actually it's a little anticlimactic at this point. So the equilibrium concentration of nickel is going to be, well, x. So 2.9 times 10 to the minus 8th molar, that's the equilibrium concentration of nickel. Ammonia is going to be 0.50 plus 6x. Well, guess what? With sig figs, that x doesn't even matter. So the equilibrium concentration of ammonia is the same as it started. And the complex ion is also, because it's so small. So the final answer to the problem is equilibrium concentration of nickel is x. Equilibrium concentration of ammonia is 0.50. Equilibrium concentration of the complex ion is 0.25. All of that is done strictly to make the 5% rule work. Okay. I think that's where I'm going to stop this, but I'm looking at your homework right now, because this should be the end of the week, and what should you be able to do? Okay, I'm just going to kind of run down some of these problems, give you some hints here. So question number 14 is a large equilibrium constant. Yep. Question number 14, I don't think has you do the 5% rule here. Well, it makes you do a qualitative discussion. You should be able to handle number 14. Number 15 is where you go through some examples where you apply the 5% rule and where you don't. So I think that'll be okay. And sometimes you're given moles and liters, so you have to calculate molarities. And some of these I give you the answers. And one of them I have you use pressures. and 15 part B. Don't convert pressures into molarities. Just use the pressures and use a KP rather than a KC. And your answers are going to be atmospheres rather than molarities. That's fine. C is the 5% rule and the long way to show you get the same answer both ways. Number D, yes. So the two problems that this applies to are, let's see, 15D and 16 will require you, I'm pretty sure, to do something like this. So 15D, the chemical equation is given to you. 16, the chemical equation is not given to you, but you're given the chemical formulas for the two reactants and the product. You're doing a synthesis. Make sure you balance the equation properly. And the answers are given to you there. Okay, folks, rock on. This is a lot. So this is doing a lot of problems. So don't wait on these and let me know if we need to set up a Zoom tutoring session. Otherwise, I think we're going to be good to go. And that, folks, is chapter 13, which was a big one. So good work. Keep it up. And I'll see you sometime soon in chapter 14.